Hello everyone. In this lecture, we will continue the previous study of solving the closed formula for the recurrence relations. And recall that last time we deal with a case when the characteristic equation has distinct roots. And a natural question is, what if the roots not distinct? There might be some repetition. So what should we do? So mathematically, that means suppose the relation, the characteristic equation related to the relation has repeated roots. How to find a general solution for Hn. And we start with an example. So suppose you have the following recurrence relation of order 3, and the initial data is -2, -6, and 0. And so first, we consider the characteristic polynomial or equation, and you can factor it, find that this will be x minus 2 times x squared minus 4 equals 0. Furthermore, you get x minus 2 squared times x plus 2 equals 0. And from previous study, we know there are two special solutions, 2 to nth power, -2 to nth power. Okay, now if we set up the general solution as Hn theta C1 times 2 to nth power plus C2 times -2 to nth power, and then you plug into the initial data, you get -2 is H0 is C1 plus C2, -2 is H1 equals C1 times 2 plus C2 times -2, 0 is H2 equals C1 times 2 squared plus C2 times 2 squared. And from this, you get no solution. So what's the problem? Because you have, in general, like this type of problem, you have more equations than variables. And from linear algebra, we know, in general case, that will give you no solution at all. Okay, so what does that mean? That means your special solution are not enough. You only have less special solution than the initial data. Okay, so the idea is we need to find more special solutions. So that's a key observation or key motivation in this type problem. And here, let's consider n times 2 to nth power instead of 2 to nth power. And what do you have? And plug into the recurrence relation. We have n times 2 to nth power minus 2 times m minus 1 times 2 to m minus 1's power minus 4 times m minus 2 times 2 to n minus 2 power minus, plus 8 times n minus 3 times 2 to n minus 3's power. Okay, and here, factor out 2 to n minus 3, you have 8m minus 8m minus 1 minus 8m minus 2 plus 8m minus 3. It's 0. Therefore, we have a new special solution. N times 2 to n's power. Okay, now if we set up the general solution as C1 to 2 to n's power plus C2 times n times 2 to n's power plus C3 times negative 2 to n's power. Okay, then you plug into the relation, plug into the initial data. We have C1 plus C3 is negative 2. C1 plus C2 minus 2 times C1 plus C2 minus 2 C3 is negative 6. And C1 plus 2 C2 times 4 plus 4 C3 is 0. And now you have 3 variables and 3 equations. In general, you will have a solution. So here you solve it, we find that C1 is negative 3, C2 is 1, C3 is 1. So Hn is n minus 3 times 2 to n's power plus negative 2 to n's power. Okay, and the above method actually can be generalized. So we state the following theorem. Suppose you have a recurrence relation of order k. Okay, and consider the characteristic equation xk to k's power minus a1 times x to k minus 1 minus ak minus 1x minus ak. Have factorization x minus q1. Let me write here. X minus q1 to s1, x minus q2 to s2, all the way to x minus qt to st, where q1, q2 to qt are distinct. S1, S2, St are positive integers. Then the general solution star can be given by C11 plus C21 times m plus all the way to CS11 n to S1 minus 1 times Q1n and plus C1 2 plus C22 times n plus all the way to CS22 and S2 minus 1 Q2n plus all the way down to C1t plus C2t times n plus CSTT times NST minus 1 times QT to n's power. So you see, whenever you have, for example, for each root, let's see, Q1, since you have S1 repeated roots, so here you should have a polynomial of degree S1 minus 1 less. So the polynomial in M. Okay, so that's a general rule. And then for each given H0, H1, K minus 1, there are constants C11, CS11, C21, CS2, C12, CS22, all the way to C1, T, CSTT, such that the star is a unique solution according to the relation and the initial data. So that tells you this method is good enough. Whenever you put in some initial data, it gives back a solution corresponding to the data and the relation. A small remark is, actually this is also how we solve ODE. If you learn the ordinary differential equation theory in some course, this is exactly the method they use there. So basically, there's no difference. I view this as a discrete version of the ODE. Okay, later we will not talk about the Stirling number and the difference quotients, which is very useful in numerical analysis. But I suggest you to read the corresponding sections in chapter 8. So therein you will find the discrete version of the ODE, and you can compare it with the method we use here. Okay, now we are done with the method solving the homogeneous constant coefficient relations. And now, what if we still have constant coefficients, but we have non-homogeneous term? So that problem will be more difficult, and basically there are no general method. So the problem is just as before, you have the recurrence relation, which is a polynomial, but here you have some other constant. So you have this extra constant. Therefore, previous study is not sufficient. It gives you partial result. you're still missing one key step. Okay, why we care about this? So to illustrate this, we introduce the following very interesting puzzle, which is called Towers or Hanoi puzzle. So there are 3 pegs and circular discs of increasing size on one peg with a largest disc on the bottom. So the larger one are on the bottom, and these discs are to be transferred one at a time onto another peg with a provision that at no time one is allowed to place a larger disc on top of a smaller one. And then the question is determine Hn, the number of moves necessary for the transfer. And we can first draw a picture. So you have 3 pegs, and so if you have one disc, then this is easy. So you just move this one to new place. Okay, and suppose you have so that just means for convenience H0 is here. So if you have one disc, then you only need one step, one move to transfer it. And if you have 2 discs, then first you can transfer the smaller one to a new place here, and then this is first step, and then transfer the the larger one to second peg, and the last step transfer the smaller one back to the second peg. Therefore H2 is 3. Okay, and what about the general case on observation is that n discs you can do in the following way. Step 1, move the first n-1 discs to the second peg. Step 2, move the nth disc to the third peg. And step 3, move the first n-1 disc to the second peg. Okay, and after this reduction, you will find Hn should be 2 times hm minus 1 plus 1. So usually the constant term comes from some small correction, just like think about it for the derangement. We will talk about later. Derangement number. So you have some geometric part, just like it's a geometric series, but also you have an extra term, extra 1 in some relation. So here you have extra 1 here. And for this problem, actually you don't need some advanced method. We just plug in, and you will see the pattern. So this will be 2 times 2m minus 2 plus 1 plus 1. And therefore it's 2 square hm minus 2 plus 2 plus 1. And if you further plug in, this will be 2 cube hm minus 3 plus 2 square plus 2 plus 1. And all the way to m minus 1 h0 plus 2m minus 1 plus 2m minus 2 plus all the way to 1. And since h0 is 0, this will be a summation or geometric series, so 2m minus 1. Okay, before we study the general method, let's talk about a little bit about the general case of the Hanoi puzzle. So how about 4 or more pegs? So here is a frame Stewart algorithm. So suppose you have n disks and r pegs, and define T and R to be the minimum number of moves required to transfer n disks using R pegs. And the algorithm goes as follows. So step 1, for some t, for some k to be determined later. For some k between 1 and n, transfer the top k disks to a single peg other than the starting or destination pegs. And this takes TKR moves. And then step 2, transfer the remaining m minus k disks to the destination peg using only the remaining r minus 1 pegs. So this step take T m minus k r minus 1 moves. And step 3, transfer the top k disks to the destination. So this step takes TKR moles. So what is TNR? So recall that in the previous algorithm, you have an undetermined variable k, and since t, we mean the minimum. So this will be the minimum for all k between 1 and r minus 1 to TKR plus Tm minus k r minus 1. Okay, the algorithm is pretty clear, but this result just know very recently. I don't know if the proof is correct, but probably you can see Wikipedia for the reference of the proof. Because our algorithm didn't actually show you that from this procedure you do have the minimum TNR. Okay, so probably it's also a good idea to do some reading report on this topic. And okay, now let's look at more complicated non-homogeneous relation. So here, instead of some constant, you have some linear function. And so the solution is we first find the general solution for the homogeneous part. Okay, and then all you need to do is find one special solution of the non-homogeneous part. So no matter what is the relation is, you first solve the homogeneous one. Step 1, solve the homogeneous one. And you might need to use several special solutions to cook up the general solution. And here you don't solve the initial data because it's not correspond directly to the initial problem. And step 2 is find one more special solution. So here the crucial thing is you only need one special solution. And step 3 is accommodate the initial data. Okay, so here let's see the general solution. Let's see, it's Hn theta, and here the special solution. Let's see, Hn hat, and so finally the general solution for the non-homogeneous one is Hn, defined by the general solution for the homogeneous one plus the special solution for the non-homogeneous one. So with the form. Okay, and now let's look at step 2. So how to find a special solution for this one? And we guess Hn should be An plus B. And then if you plug in An plus B equals 3 An minus 1 plus B minus 4n, that gives you 2A minus 4n plus 2. This equals 3 minus 2b, 3a minus 2b. Okay, since you want this to be true for any, since this, let's call it delta. Since delta is true for any n, then A is 2, B is 3. Okay, then you will find you do have a special solution. This is 2n minus 3. Okay, now let's look at step 3. The general solution for the non-homogeneous part now becomes C times Hn delta plus Hn hat equals C times 3 to nth power plus 2n plus 3. Okay, and now consider the initial data. H0 is 2, so you plug in 0, you do have C plus 3, and therefore C is negative 1. And then the general solution Hn is minus 3 to nth power plus 2n plus 3. Okay, from the previous study, we know that the key point is to find a special solution of the non-homogeneous question. And in general, there's no systematic way, no general way to do this. And we only know some partial result. The first one is if Bn is a polynomial, then it's easy. Choose if Bn is a polynomial, choose a special solution Hn hat to be a polynomial. And here the key point is that if this is a polynomial of degree k, and here you also choose a polynomial of degree k. If it happens to to lead to no solution, then you just raise the degree one above. Okay. And secondly, if Bn is exponential, choose Bn also to be exponential. And probably from these two, you might guess useful idea that whenever you see the constant part, the non-homogeneous part Bn has some form, and you guess your special solution also has that form with different coefficient. And after plug in solve it, you can accommodate your coefficient to figure out a solution. And you don't need to figure out all the non-homogeneous solution. You just need to, so all the special solutions, you only need one. Remember that, because the homogeneous part will give you more information. Okay, now for Bn to be a exponential function, we also give an example. So suppose you have this, and the general solution for the homogeneous part problem is Hn theta equals c times 2 to nth power, and then the special solution to non-homogeneous one is Hn hat equals, we guess probably you have p times 3 to nth power. And then you plug it in, you will find it's p times 3 to nth power equals 2 times p times 3n minus 1 plus 3 to nth power. And then you have 3p equals 2p plus 3. P is 3. Therefore, the general solution Hn is Hn, the general solution plus the special solution. This is c times 2 to nth power plus 3n plus 1. And note it, now we accommodate the initial data. So the initial data is 2 equals h0. And this, on the other hand, by the formula is c plus 3. Therefore, c is -1. Hn is -2 to nth power plus 3 to n plus 1's power. Okay. So that's how we solve the non-homogeneous ones. And probably I need to do make a remark. So here, guess similar form. Okay, next we turn to another topic, which is called generating function. This can give you another way to solve the recurrence relations with constant coefficients. On the other hand, this idea is widely used in probability and in economics, because at that time, when you want to, there's some so-called momentum generating functions when you want to prove the central limit theory or some advanced probability theory rigorously. You do need some more advanced mathematical tool. And the idea is very simple. That is, previously we view all the sequence H0, H1, H2 as separate things. You have a lot of things. But now you cook up some function, a single function, incorporate all the data. Okay, and when you compare this sequence with another one, what you are doing is just manipulate the single function with the single function corresponding to the other sequence. So this is more convenient. You just view the data globally. You have better organization of the data. But of course, the key point here from the later discussion you will see is how to incorporate the data, how to construct the generating function. And the key point for the proof usually is always a clever way to do that. And here we will introduce two methods. One is called just generating function, and the other one is called exponential generating function. Okay, so that's the motivation. So given a sequence numbers Hn, it's not necessary to be just the numbers. It could be some variables, some kind of probability measure or whatever. So corresponding to a situation you have. And then the corresponding generating function is gx equals summation from 0 to infinity. And here you have Hn times, here you have x to nth power. So x is a formal variable. Okay, and now let's look at some easy examples. Suppose Hn is 1, and what do you have? You have your generating function, then is summation 1 times x to nth power is 1 over 1 minus x. Okay, here, of course, this formula should be understood in this way. That is, when this sequence is convergent, but in the combinatorial, at least in our course, the convergence is not that important. You can always assume the absolute value of x is very small. Therefore, the sequence do convergence. Okay, second way is suppose you have 1 over n factorial, then your function gx is x to nth power divided by n factorial. So this is exponential x. And if you have Hn equals m, choose m. And here m is fixed. Then gx is summation of m choose n times xn's power. And by the definition, actually, this summation now is finite. That means you only have finite terms, and it gives you 1 plus x to n's power. And another example is, so suppose you have fixed k, and for n non-negative, define a number hn to be the number of integral solutions of the indeterminate linear equation y1 plus y2 all the way plus yk is n, and each y is non-negative. And what is the generating function gx? I will give you two solutions. So first solution is, we already know hn is n plus k minus 1 choose k minus 1, or n plus k minus 1 choose n. Therefore, you plug in gx is summation for n from 0 to infinity, n plus k minus 1, n x to n's power. This is 1 over 1 minus k to k's power. By Taylor expansion. Or if you don't know what is Taylor expansion, please look at the Wikipedia. And the solution 2, we noted that 1 over 1 minus k is 1 plus x squared plus all the way to infinity. Then 1 over 1 minus k to k's power can be written down as follows. Summation for y1 from 0 to infinity, x to y1's power, and then we do the same thing for replacing y1 by y2. And finally, y1 by yk. And you combine each term. You do the distribution law. You do have the summation for y1, y2 to yk are from 0 to infinity. And then inside, the summand is x y1 plus y2 plus all the way to yk. So this is the form, this is the form we like, or appear in the equation. Okay, now you sum in a different order. That is, you sum in the following way. For let me see. Rearrange the summation by the index by the power of x. So for you combine all the terms with same power in x. So x to n's power, and then inside will be just the number of integral solutions of the equation. Okay, then by definition, this is just gx. Okay, now let's look at a little bit more complicated question. Suppose Hn is a number or integral solutions of y1 plus y2 plus y3 plus y4 equals n. And each variable is non-negative. y1 is even, y2 is odd, y3 is less than 4, y4 is greater than or equal to 1. And then what is the corresponding gk? And from the second method used in the above example, we know that the generating function can be written in the following way. So here, y1 is from 0 to infinity, y1 is even, xy1. And y2 is from 1 to infinity, y2 is odd, xy2. And y3 is from 0 to 4, xy3. y4 is from 1 to infinity, xy4. And then if you expand, you do have the following product or infinite sequence. Oh, sorry, the third one is finite. Okay, and then for each one you do have a formula. So for first one you have 1 over 1 minus x squared. And then for second one you do have x over 1 minus x squared. And then for third one you just keep it. And for last one, you have x over 1 minus x. So finally, you do have, this is x squared 1 plus x squared plus x3 plus x4 divided by 1 minus x cubed times 1 plus x squared. And then if you use if you use partial fractions, you need to solve equations, but I will just give you the result. You have this two fractions. Okay, and actually, so I will make a remark. Actually, we can write down an explicit formula for Hm, but it's tedious, and if we care about only whenever you have something tedious, think about a limit, just like in computer science or in probability. Even if you don't know each small detail, we can still guess a bigger picture. And so the interesting part is we can talk about the limit. It's not a limit. Sorry. The limit is always 0. What is asymptotic behavior of Hn when n goes to infinity? In other words, what is a leading term of Hm? From the previous formula, we know that Hm must be a polynomial. And for the leading term dominates asymptotic behavior when n goes to infinity. So it's the most important one. And from the formula, we do have the information of the leading term. Okay, and now I give you some easier example, which where the actual Hn can be derived. So Hn still the number of integral solutions of the equation y1 plus y2 plus y3 plus y4 equals n, and each one is non-negative. Y1 is even, y2 less than 2, y3 is a multiple of 3, y4 is less than or equal to 1, and what is Hn? So Gx is 1 plus x squared plus x4 plus times 1 plus x squared plus 1 plus x cubed plus x26 times 1 plus x. This is by a similar argument as before, how we interpret the generating functions. And now, if you sum them up, you do have this. And actually, this problem is very tricky. Not very tricky, just by chance, you do have a lot of cancellation. So for example, if you cancel out with this one, you do have 1 minus x. And you cancel out this one, you have 1 minus x. Therefore, finally, you have 1 minus x squared. And you expand it, you will have, this is n plus 1 choose 1 x to n's power. Okay, therefore Hn is n plus 1 kind of. Okay, and this is how we use the generating functions to have some actual computation. There are also some cases we just use the generating functions as a theoretical method to do the proof. So suppose we want to create a set of weights so that any object with an integer weight from 1 to n pounds can be balanced on a one-sided scale by placing a certain combination of these weights. So on that scale, so what is fewest number of weights we need? So the problem, we can draw a picture just like you have a scale, okay, and you can only put your weights on one side, so that's the so-called one-side scale. And so that on the other side, no matter what objects you have, as soon as it's from 1 to n pounds, it can always be balanced. Of course, here we assume the weight is integer pound. Okay, and the solution is first for this type of question, like in combinatorics or in other problems, whenever you ask for some optimal situation, you have two tasks. First is to construct an actual scheme or the actual plan, achieve that bound. And secondly, you need to prove that, you need to show that anything beyond that is impossible. And here we use two-digit numbers to construct it. Suppose your weight is weights are as follows: 1, 2, 2 square all the way to 2 to log to n. And take the integer or the floor or log to n. So you total have log to n floor plus 1 weights. And it is clear that any k between 1 and n can be written as k from 0 to log to n floor ak times 2 to k's power, where ak is 0 or 1. 0 means you don't choose that weight. 1 means you put that weight on the right hand side. Okay, next we need to show that this number is minimum. And we prove by contradiction. Suppose we only need k weights, a1, ak, to do the task, then we can construct the generating function okay, and know that hn is greater than or equal to 1 means we do have a method to balance. So here ak, sorry. Oh, bad notation. M HM XM to balance object with weight M. Okay, also, but noted that on the left hand side, due to the distribution law, we have at most 2 to k's power non-trivial coefficients of x to m's power. Okay, then we have 2 to k's power minus 1 should be at least as many as m. So here minus 1 because you have a trivial term, constant term. 1 here means you can always put nothing on the scale, which measures 0. Okay, so it's outside of 1. outside the weight from 1 to n. So you do have this, and then k at least log 2n plus 1. So we are done. Okay, and another related one, which shows that this method is actually very, very interesting, is if we change one side to two-sided, which means that you are allowed to put weight on both sides. For example, here you also have a small one here, and you have objects here. Okay, and what is the minimum? So the idea is we can consider the weights 1, 3 square all the way to 3 log 3n floor. And the idea is, so here, even to show that you can always do this, is not that trivial. So we, at the very beginning, we use a generating function. So the generating function can be written down as this way. And then you see the interesting part. So the generating function not necessary to be a polynomial or infinite sequence of polynomials. It can also have some negative part, so the fraction part. Three to m, and this will be summation from negative infinity to infinity. So here the summation is just formal sum, and we can have at most 3m to m non-trivial coefficients. But how do you know we can always balance each weight between 1 and n? So from this, it's not that easy, because in the one-sided case, every number has a bi-digit representation. Okay, but here, it's not that trivial. But from the generating function, we can prove it directly by calculate the thing. Okay, and if you factor out, you will have this, not factor out, you will write it. And if you combine the denominator, you will have x1 plus 3 plus all the way to 3 to m's power. And then you times 1 minus x with the 1 plus x squared. And then the tricky part is the product is 1 minus x cubed. Okay, then if you combine 1 minus x cubed times 1 plus x cubed plus x to 6, so this is 1 minus x to 9. And then you can combine x to 9 with the next term. So finally, you will have, this is 1 over x1 plus 3 plus all the way to 3 to m's power times 1 minus x times 1 minus x 3m plus 1. Okay, now we compute the first denominator is x to 3 m plus 1 minus 1 divided by 2. And the second one is 1 plus x squared plus all the way to x 3m, 3 to m's power. Okay, and then if you distribute it, you will have this is x minus 3m plus 1 minus 1 divided by 2 plus x minus 3m plus 1 minus 1 divided by 2 plus 1 plus all the way to 3m x to 3m plus 1 divided by 2. And then we see that we can weight each weight between 1 and n. Okay, and so we end up with this type of generating function by the following example, which gives you another way to solve the non-homogeneous recurrence relation. So we set up the generating function and we use 2x minus 2x gx. Then what do you have? And by computation, you find this is 2 plus 3x plus 3 square x squared plus 3 nxm plus all the way down. And then this is 1 plus 1 over 1 minus 3x. Okay, and then you can solve gx is 1 over 1 minus 2x plus 1 over 1 minus 3x times 1 minus 2x. And this is minus 1 over 1 minus 2x plus 3 1 minus 3x. And then you expand each one. You can get the explicit formula for Hn. And the answer is the same as before. Okay, now we introduce another type of generating function. This is so-called exponential generating function. So suppose you have sequence Hn, and the exponential generating function is defined by summation for 0 to infinity Hn times, instead of x to n's power, you just put n factorial in the denominator. In other words, you normalize the sequence before you put it into the generating function. It's called it's exponential generating function. And then we have some easy examples. So when Hn is constant sequence 1, then the generating function is just exponential x. And another example which illustrates the reason why we introduced this is that for non-negative integer n, for k between 0 and n, let hk be the number of k permutations of 1, 2, 3, all the way to n. Okay, then what is a generating function? Recall that actually here we can compute hk, which is product from n to n minus k plus 1. This is pnk, or n factorial divided by k factorial. And then the generating function is n factorial n minus k factorial 1 over k factorial times xk. So this is summation infinity nk xk So this is 1 plus x to nth power. And you see here, kind of the exponential function is designed for the permutations, because for the permutation, you always have m factorial here. Okay, and then you have actual m k factorial here, so that will give you some good combinatorial numbers. This is just backwards reasoning why we design this. But when you do actual research, you should try all the methods you have until you get a expected result or your ultimate goal. There's no common rule. Okay, and so let's look at a little bit complicated example. So fix k and consider the multiset n1 times a1 all the way to nk times ak. And for m non-negative, let hm be the number of m permutations of the multiset star. And then what is generating function gx of hm. So first, recall that what is hm? We already know that hm is summation of m factorial divided by b1 factorial, b2 factorial, bk factorial for all b1 to bk, such that the summation is m, each bi is between 0 and ni. And the exponential generating function is a summation for m from 0 to infinity, hm xm divided by m factorial. This is for m from 0 to infinity summation. You have some constraint for bi, xb1 plus all the way to bk divided by b1 factorial, b2 factorial, all the way to bk factorial. And this is, you can decompose the summation into each variables b1, b2, bk. bk, nk, x to b1 plus b2 plus all the way to bk divided by b1 factorial, b2 factorial, all the way to bk factorial. And then you can further break it by distribution law, b1 factorial, b1 and n2, x b2, b2 factorial. Finally, you have bk factorial. Okay, so we are done here. And here you see why we use the exponential function is, let's look at exponential generating function is because after that you do have cancellations, because here actually you have m factorial, you have m factorial 1 over m factorial, and you have cancellation. So the generating function itself So the big remark is generating function have two aspects. First, no matter which type of generating function, it include all the information or the sequence Hn. So this no doubt, no matter which type of generating function you choose, the first step is always true. But second step is a crucial one is that for different problems, we should choose a suitable generating function which is easy to compute. That means it's better to have a closed formula instead of a messy. Okay. Now let's look at the following example. So let Hn be the number of ways to color a 1x board with colors red, green, and blue. Such that firstly, the number of red squares is even. Secondly, there is at least one blue square. And the question actually is easy, and but the key point is you need to decide which generating function you are going to use. So here, if you already decide you are going to use the exponential one, then you can do the following. So this is a generating function. And this is a red part. This is a green part. For green part, there's no restriction. And for the blue part, you miss the first coefficient. Okay, and then you can compute. So exponential x plus exponential negative x divided by 2 times exponential x times exponential x minus 1. Okay, and then finally exponential 3x minus exponential 2x plus exponential x minus 1 over 2. And then now you can write down the coefficients. So you have this by the formula for exponential functions. Okay, and then you have 1/2 summation from 1 to infinity, 3n minus 2n plus 1 over n factorial x to nth power. Or if you don't like, you can move n factorial to this side. Therefore, Hn is 3n minus 2 to nth power plus 1 over 2. And H0 is 0. Okay, another example is, suppose Hn is the number of n permutations. Of the multiset infinity 1, infinity 3, infinity 5, infinity 7, infinity 9. And such that the numbers appear an order number of times. Each appears an order number of times. And the solution is easy. For generating function, we can manually write down it's a x plus x cubed over 3 factorial plus x to 5 factorial plus all the way to infinity and fifth power. And this is exponential x minus exponential negative x, fifth power. And this is exponential 5x minus 5 exponential 3x plus 10 exponential x minus 10 exponential negative x plus 5 exponential negative 3x minus exponential minus 5x divided by 32. And then hn is 5 to nth power minus 5 to 3 times 5 times 3 nth power plus 10 minus 10 times negative 1 to nth power plus 5 times negative 3 to nth power minus negative 5 to nth power divided by 32. Okay, so we're done. I will stop here for this lecture.